Can you hear me properly?
Yes, sir. You are very much
Yeah.
audible.
Yeah. Okay. So that was of course, this biophotonics and green photonics are more active areas for my research, and so Dr. Nirmal chose the biophotonics first. So today I will talk about this optical nanoscopy and quantitative phase microscopy. Both the techniques are very, very important. And my lab's name is basically Biophotonics and Green Photonics Laboratory, Department of Physics. So I will begin with this chart. You can see that on the top here. So let me put the laser pointer first. Okay. Yeah. So you can see here, you could see my slide properly. Hello.
Yes, it is
Yes, sir.
properly
Yes, sir.
visible.
Yeah. So I'll begin from this. You can see this scale is starting from left to right. It is a scale of 1 millimeter, then 100 micron, 20 micron, 10 micron, up to sub micron level here, 1 micron, this one. Finally, a angstrom level, 1 angstrom. So if you look at the various kind of sub objects in around us, so you can see small ants which is of the size of 1 millimeter. Then human eye, human eye is the first imaging device, and we can see the smallest object size is something like 100 micron, and that is the diameter of the human hair. So beyond this size, 100 micrometer, we cannot, and this is the spatial resolution of human eye. So we cannot see anything smaller than this 100 micron. And also our eye also has a temporal resolution, which is about millisecond or 100 milliseconds, something like that. So you cannot see any fastest event that. So these are the two limitations we have in our eye. So then the scientists build this microscopy. The first comes is the wide field optical microscopy, which has been there for the last several centuries. I will give you one brief history of microscopy also. Then this microscope, optical microscope, means all kind of dark field, bright field, fluorescence microscope, and this what is called even confocal microscope. So they walk in this range. So confocal microscope basically slightly improved. You can get slightly improved result up to sub micrometer, about 500 nanometer, or most probably basically can go to 250 nanometer. So in that range, with these two microscopes, you can see now we can easily see the human red blood cells and white blood cells. So red blood cells are of diameter 7 micron, 6 to 7 micron, thickness 3 micron. White blood cells are something like about 10 micron, and then go down to 1 micron or submicron level. You could see the bacteria. Or so mostly people use these microscopes for looking at E. coli bacteria is most commonly used. So though the size of E. coli bacteria is in this range. And then look at this virus beyond 200 nanometer, beyond 200 nanometer, which is the range of 200 to 150 nanometer. So this is the range where optical microscopes like bright field microscope or laser confocal microscopes cannot see these things. That is why the difficulty right now in the corona pandemic, we cannot see any viruses with these microscopes. And the sizes of typical size of coronavirus, if I talk about, is 100 nanometer, and they are of course up to 50 nanometer also there. So this is the size of various kind of viruses, SARS, CoV-1, CoV-2, all these viruses are in this range. So then for imaging right now, of course, you could see them in the newspapers and in some journals, the images of the virus, coronavirus. So this is the bottommost, right bottommost, you can see my cursor. So this is the image taken by electron microscope of a coronavirus. And since diameter is of course 100 nanometer, but around that it has a spike protein, which is just 1 nanometer or sub nanometer spike protein. And that was the necessity to image this virus with the help of a electron microscope. So then can we see these viruses with the optical microscope? Answer is right now no, but this is what is the topic today, that there is a technique called optical nanoscopy or super resolution optical microscopy. We can see now, of course, up to 100 nanometer, up to 50 nanometer. So they have been used for viruses, but other objects they have been used. So you can now in this scale down below 50 nanometer, what is the 10 nanometer protein structure, single molecule, basically 1 nanometer, 10 nanometer, 5 nanometer molecule protein. And then finally you have single atom. So this range around 10 nanometer to 1 angstrom is basically all these microscopes, atomic force microscope, scanning electron microscope, tunneling electron microscope, scanning near field scanning optical microscope. They are very popular, and with the help of these microscopes, you can virtually see the single atom defects in the graphene, for example. All these things can be seen, and they are very popular in material science, all these techniques. But in biology, I will show you later on also. And in biology, the super resolution microscope, electron microscope, EFM, they are not very friendly, because we biologists would like to see the nanostructures or cell structures or membrane fluctuations in the live condition, because for imaging such a super resolution, with such a super resolution, all the living cells and living objects have to be first dead, killed, frozen, and sample prepared. Then only you can see. But biologists always prefer to see them live. But so if you want to see them live, then you cannot see these techniques. They require a special sample preparation. So what is the choice? Choice is again optical microscopy, but optical microscopy, normal wide field microscopy or confocal microscopy suffers a great limitation, what we call a diffraction limited resolution. Diffraction limited resolution. So these microscopes cannot see, and scanning probe microscopes cannot be used for nanostructures, because we want to see living cells without damaging them. So that is why the scientists kept on working, many biologists and optical scientists, to break this diffraction limit. So what is this diffraction limit? You can see here extreme left down. So if you tightly focus white light is a visible light. So if you tightly focus with the highest possible numerical aperture objective lens to the small spot, so you can see in the lateral direction, this, if you take the cross section of this focus spot, which is about 200 nanometer, in the axial direction, it is something like 500 nanometer of a wavelength of light, 500 nanometer. So then, so that looks one spot, one bright spot. So suppose if in this size of, in this volume of the focus spot, there are several 50, 100 nanometer nanoparticles, for example, or nanostructures, they all will be seen as if one. So this microscope cannot see, and that was the diffraction limit set by Sir Abbe, Ernest Abbe, and this is what is called Abbe's limit. And then he was a German scientist, and then this limit was, of course, true and is a fact. And then, of course, that is why people also believed, and also fact. Then this was erected on a stone in somewhere in Germany, Heidelberg, down the street on this. If you visit somewhere here, I borrowed this from Nobel laureate's lecture. And then here at the middle, it is written D equal to lambda by 2 n sine alpha, which is lambda by 2 Na. So it means all the optical microscope cannot see objects smaller than this. And moreover, diffraction limit is also posed here, all because moving electron, because electron microscopy or these are also using the electron beam for focusing and all those things. But I'll show you why we could see such a small object with this. So today's topic is basically, first part is optical nanoscopy, not all these probe microscopes. So how to break the diffraction limit, how to go beyond the Abbe diffraction limit, and we can now, with the help of this optical super resolution nanoscopy technique, we can see the object something like 100 nanometer, 50 nanometer, even sub 20 nanometer they have also reached. So this is the topic today we are going. So look at in the history of the Nobel Prize in this field. So that Nobel Prize awards in this area of microscopy. The first goes to Jernak's phase contrast microscope, and which was 1953. And then in 1971, Dennis Gabor got a holographic Nobel Prize for holographic microscope, what we call lensless microscope. And then after, so these two are basically phase contrast microscopes. That is why my second part will be the quantitative phase microscope. So these two techniques, Nobel Prize fields, are basically the foundation for quantitative phase microscopy, and they are basically phase microscopes. And then, of course, Nobel Prize in Physics 1986 goes to the scanning electron microscope group, and these three scientists. And you can see after that, 1986. So this is the Nobel Prize in Chemistry 2014 was awarded jointly to these three scientists, Eric Bedwig, Stephen Hell, and Moiner, and for the developments of super resolved fluorescence microscopy. Of course, all the techniques are optics and physics, but Nobel Prize given in the chemistry, because chemistry they looked at a single molecule of fluorescence. So this was that one. It is basically optical nanoscopy, and more recently 2017 is awarded by to these people developing the cryo-electron microscopy. So 2 in cryo-electron, 3 optical microscopy, nanoscopy. So quite enough Nobel Prize awarded in this field. So now with this so many Nobel Prizes in this field, so let's look at the history of the microscopy. So it goes back to 1519. Actually, we in a general knowledge question, we always answer a question they ask, who was the first inventor for the microscope. So we say, of course, Leeuwenhoek. But you see, before Leeuwenhoek, so this Zacharias Janssen and his father and sons, they basically experimented with the lenses. They put there are several lenses in a tube and made a very important discovery. And their maximum magnification was around 9x, but they did not popularize too much, so they were left. So actually, the beginning comes from 1950s. The same time, Galileo Galilei was basically building the telescope, and they were making the microscope for downwards and the telescope for upwards. So you can see the almost similar time the two big things were happening. But of course, von Leeuwenhoek was given the credit for first optical microscope. This is a structure of this one. You can see in many textbooks this one. And more famous, this microscope became more famous after the Robert Hooke's modified version, in which he had used both basically objective and all those things, and he imaged bacteria. So basically in 1665. So this is the beginning. So these are the pioneering or most early version of the work. So let me give you some idea about a simple microscope. Basically, the magnifier. We are all familiar with this one, and that we call hand lens. So this is also a simple microscope. So the microscopic condition is basically if you have a lens, powerful lens or magnifying glass. So if you place object very close to the lens, basically within the focal length, at focus or within the focal length of the lens, it will always act as a magnifying glass. So you could see small object to big. But this simple microscope will give you only 50 micron resolution. You cannot see anything smaller than this. So this is, of course, very familiar. So most the appropriate and most familiar, widely used microscope we call is the compound optical microscope, and is also called wide field microscope. In this, you see here the condensed light coming from behind. If you have a parallel light, then you have a condenser lens, and you focus light on the object, let's say a 1 micron bacteria, for example, E. coli bacteria, and this bacteria on a glass slide will scatter light, and scattered light will be collected by this objective lens, and this objective lens can be very powerful. Up to maximum magnification is 100x, and maximum numerical aperture is, if it is a oil immersed objective lens, that can be 1.40 numerical aperture. And then you see again the same condition, the object has to be exactly at the focus or within the focus. And then this is basically this is a 4F imaging system, and the first magnified image by this lens will be built somewhere in the tube of the microscope. That is why you see long tube on the top of the microscope, very long tube, that is normally 18 centimeter, 20 centimeter, or something like that. And then that is the inverted image, but magnified how much? 100 times, because 100x. Now this inverted image, so you still see this one micron became 100 micron, that you will barely see with the naked eye. You further need to modify or magnify it. Then you have to use another powerful lens, which we call is eyepiece, and some people also use here tube lens. And eyepiece will be basically now further magnifying it, because the image, inverted image, which is first stage magnified, is within the focal length of this eyepiece, and hence this becomes an object for eyepiece, and if further magnified, and it magnified image looks like this one. So 1 micrometer object here will be seen 1000 micrometers. So 1000 micrometer means 1 millimeter. So that is why we could see easily bacteria or RBC, WBC on our naked eye with the bright field microscope. So it's basically two-stage magnification plus, of course, length, tube length also matters. And then the magnification, you already know the total magnification we calculate with the microscope is this one. So for this 1 micron object, it becomes 1000 micron. And then resolution is given by this formula. I will come back to the next slide. So this is how we could see 1 micron up to sub-micron particles with the bright field microscope, and with the help of the most powerful lens, what you call is the numerical aperture, if it is oil immersed. If it is a dry, the maximum numerical aperture is 1. If it is oil immersed with the help of oil, this becomes 1.4. And then you can also match this objective lens. The condenser also can be same specification. Then that microscope becomes highest possible magnification, highest possible resolution. This is what is the condition. So, but this microscope is, as I said in the first slide itself, it is having the limitation of diffraction limit, and that is what is you have seen in the previous. So we calculate two kind of resolution: lateral resolution, axial resolution, and that is how it is 500 nanometer. So if you look at this one, so if there is a protein structure, for example, like green fluorescence protein, and which is of this kind of structure, and the total size is about 2 nanometer by 2 nanometer, so you won't be able to see so within that volume. So they all will look one. And same thing applied to fluorescence microscope, and even if it is confocal also, that will be slightly improved resolution, but it will, fluorescence microscope will also collect fluorescence from each volume of this one, and it will show only one. So this is the problem of the bright field microscope. And what is this problem? Basically, Rayleigh criterion of resolution we apply. So normally formula for microscope we write with this one, 1.22 lambda by numerical aperture of objective plus numerical aperture of condenser. Normally you choose lenses. These two lenses are very important for resolution. So we choose equal optical properties like numerical aperture same and magnification same, and that can be easily obtained with the help of a reflection mode microscope. So then the final formula becomes like this one. So 1.22 lambda by 2 Na, and which is given by 0.61 lambda by Na. So this is the resolution formula for a microscope. So if there are two nanoparticles very close by, then if your microscope cannot resolve, then the microscope will see just one object like this one. and surrounded by ring structure, what you call the diffraction pattern. But if your microscope is little more powerful, then you could see this kind of structure. That is what you call is a Rayleigh criterion of resolution, when the intensity maxima of one object side by side is coincided with the first minima of the second object, then the two object point can be set, they are just resolved. You may conclude here that, well, it appears to me there are two particles, but this is not a clear-cut resolution. So this is the limit of what we call is the Rayleigh criterion resolution limit. But if your microscope is more powerful, then you can see clear-cut two objects, but surrounded by diffraction pattern. So diffraction is always coming into picture. So this is what is the problem of the all bright field microscopes. Hello.
Professor Mehta.
Yeah. All right.
Yes, it's going perfectly fine. Please go ahead.
So otherwise, I would just keep on speaking, and nothing will happen. So
no.
Okay. So what is this diffraction limited resolution? Basically, the light is, of course, we know, all of us know, light is an electromagnetic wave, and diffraction limited resolution due to the wave nature of light. So light gets diffracted, scattered whenever it passes through small objects, edges and corners, with the sizes comparable to the wavelength of light. And this all scattered component from, let's say, if you are focusing light on a small virus or small RBC particle, and that particle will scatter and diffract light all, then you will create a lot of frequency or special frequency component. And look at here an example. Suppose you have a 2 nanometer particle, and then if you try to look at this 2 nanometer particle with a high powerful objective lens, what you see is the diffraction pattern like this, or rather than this one, the array pattern. So this 1.22 from where it is coming is because of the half of this full width half maximum of this intensity pattern here, and that is well known. So anything within this envelope of this one, you would see one particle only. But in nanotechnology or nano objects, so all will be embedded inside this one. So if you have a structure of small object like this, and through your with the diffraction limited microscope, you will be seeing nothing. So these are the various techniques of that was the biggest challenge, to how to break this diffraction limit of the resolution. Of course, you know now the electron microscopy is a very powerful, scanning electron microscopy, tunneling electron microscopy. They are very powerful now. And at the same time, you have other two kind of microscopes, like atomic force microscope and near field scanning microscope. There are variety of this scanning probe microscope. There are many tip and something like so many microscopes in this one. So they are, of course, there. And they are very good for nanotechnology, material science, nanoparticles, nanostructure, nanodots, 2D material, graphene, metallics, nanostructure, whatever you could say, on a glass slide, on a silicon substrate, on anything. So they are basically the dry materials. You could see them, but these techniques are not good for live biological cells, tissues, biomolecules. And why? Because the powerful electron beam will damage the cells. And we would like, and moreover, if you look at the central part of the red blood cell, what we call is the basically membrane, cell membrane, and the thickness of membrane is few nanometer, and that membrane fluctuates, and that fluctuation is again in nanometers range. So if you want to see that membrane, then you have to kill the cell and fix it on dry, basically freeze it and fix it, and then that is what you do. But so it means you cannot see the nanostructures, nanofluctuations. And secondly, these techniques require rigorous sample preparations. So what is required in biology is basically just take out the blood, put on a glass slide or put on a small media, and you would be able to see without any other preparation. So that is the requirement. That is why people in biology do not prefer all these techniques. So what was now successfully developed and it's popular now is optical nanoscopy. And in this category, you have the stimulated emission depletion microscopy, structural illumination microscopy, and photo-activated localization microscopy, PALM you call, and stochastic optical reconstruction microscopy, STORM. They also have now DSTORM, direct stochastic optical reconstruction microscopy. So I would just briefly give on a couple of these techniques, and one of the technique we are working on a D-storm, for example. So you will also come to know about that. So, and then all these techniques were given the Nobel Prize in 2014, and all these techniques have been applied for the development of super resolved fluorescence microscopy. So more details about their lecture, you can all the audience can go download basically download their video, and that beautiful video by all three laureates, and one after another. I liked it. I have watched their video several times, so they're very good, fantastic. Okay, so before going to optical nanoscopy, so let me give you briefly why electron microscope can go such a high resolution. So this is again showing those two scientists here, and this is light microscope. So light microscope, we have a light source and a condenser, then you have a specimen sample stage here, glass slide, and then you have an objective lens, then you have, of course, projection lens, we call it the eyepiece, for example, or some, you can also say the tube lens, and then finally human eye to see the object. So this is the light microscope. So exactly to match the ray path, the electron microscope people also build similar kind of ray path for electron. So electron gun here, then you have a condenser lens, basically kind of magnetic field, or then bringing down the electron beam on the sample stage, and then again it will be basically diverging, and with the help of all these they call it, I guess you can name them objective lens, but they are all magnetic elements to control the beam. And finally, of course, finally they are using light. You can see again how you would be able to, how we can see that a particle or virus, coronavirus. We have to use a fluorescent screen, electron beam striking on the fluorescent scheme. Again, we need light because our eye is sensitive to only light, so we have to use light again finally. And then, but of course resolution is very high. Similar concept is with the SEM. So why this is so? So why SEM or SEM or TEM can give us very high resolution? Again, resolution limit is same. The formula applied is same. You can see 0.61 lambda by 61 lambda by 2 NA, numerical aperture of objective lens. So you can see this is how we calculate the wavelength of an electron. So electron is basically, the first one is non-relativistic. The second one is a relativistic formula, lambda equal to h upon 2 mass of electron cube, basically charge V naught is applied potential. And for non-relativistic, and if your propagation the velocity of the electron is very high, then you can apply this one. So if you put these values here, so what you see is the wavelength of electron is very small. And depending on the potential, I think I have the next slide. Yeah, this one. For 10 kilovolt potential, so the wavelength of electron comes out to be 0.12 angstrom. And for this high potential, it comes out to be 0.037 angstrom. So you apply the value of lambda here, so you could definitely see sub-nanometer structures or atomic structures with electron microscopes. So this is what is there because of the very small wavelength of an electron, and you could really see the super resolved particles. But the only thing is that both the techniques are not good for biological cells. And another part of this microscope is basically nanoscope is basically atomic force and scanning probe microscope. So let's say you have a atomic force microscope tip, and tip size is of course very small, 10 nanometers, something like that, even smaller than that. But the tip has to be moved across the surface. So look at, if you have a glass slide on a delicate biological sample on this glass slide, and then this tip won't be able to image that, rather than it will be damaging. But of course, for material science, you could definitely see the atomic structure or defects in atoms. This is very powerful for planning. Again, this cannot be used. So this is what is required. Then, so we come back to the optical field. Means light is non-contact, non-invasive phenomena, basically non-contact, non-invasive technique, light-based technologies. So we need to break the diffraction limit. So what is the first step to break this diffraction limit? So, well, we all know the point spread function. So if you focus light on this on a sample or you try to image the sample, and then it will be always be giving you point spread function, what we call the diffraction pattern. Then this point spread function, as I showed you, has a huge volume, 200 nanometer along axial direction, lateral direction, and 500 nanometer this one. So we need to basically engineer this point spread function, and by interfering the light. So one of the first step to break this diffraction or engineer diffraction point spread function was this kind of 4 pi confocal microscopy. So light beam divided into 50-50 here, 50% light goes this path, 50% light goes that path, and those two objective lens happen to be very, very powerful. They will be basically perfectly aligning both the focus point and the sample stage, and the moment they reach at the sample stage, so this becomes like this. So you could see, of course, the 500 nanometer along axial direction could be made 100 nanometer, something like that. This is what is the first attempt to break this diffraction limit. So if you have a microscope of same objective lens without this interference, and that will have a full width half maximum of point spread function given by this dotted line. And if you now plot this cross section along this axis, so you see several lobes. So you can of course see a particle may be here and here, or several particle may be here. But it will be seen only one time. So you are losing information where there is a dark spot. So you are obtaining information only where there is a light. So what is needed is basically kind of next slide I will show you that this bright spot has to be scanned, basically shifted. So that is what is the structural illumination microscopy. Next slide I will go. So but otherwise with this technique, point spread function engineering technique, so many beam patterns have been created. It could basically improve the resolution about almost two times. So sorry. So then this is one of the Nobel laureate did this structural illumination microscopy. As I said in the previous slide, that of course scientists could with the 4 pi confocal microscope, they could basically divide the single point spread function into multiple bright spots and dark spots, but the more wide field was required to see larger area. We need to let me convey this message. In any microscope, if you want high resolution, then you are losing field of view. If you want high field of view, large field of view, then your resolution goes down. So this is what they are basically coupled. They are coupled, and that too like that. So if you want to increase one, you are losing another one. If you want to increase the other, then you are losing the one. So this is what is the problem in the previous case. So what they have come out is basically structural illumination microscopy. Then what is this? You have a laser beam, for example. Of course, all these techniques have been applied in fluorescence microscopy. So always you use either blue light or ultraviolet light or a green light. So green light, specially filtered, clean green light from the laser passes through the diffraction grating, or special light modulator, for example, here, special light. So this grating is, of course, should be special, because you need to make all three beams equal intensity, like D1, 2, 3, and they should be equal intensity. Otherwise, normally, if you shine a laser beam on a grating, transmission grating or reflection grating, what you see is the DC component. Central spot is very bright, and followed by +1 and -1. And then, of course, second order also there, but accordingly, the intensity is going down. So the grating has to be special. And that grating will divide the one input laser beam into multiple beam of equal intensity. And all the three beams are now passing through the same microscope objective, because microscope objective cannot be improved further, because the maximum numerical aperture of a dry objective lens is 1, oil immerse is 1.4, but that's beyond that it is not possible. So this is what is, so you have to use that objective which is most powerful, and then allow these three beams to pass through this objective lens. So objective lens will tightly basically converge all three beams into a small spot, And at that spot, you will see this pattern, this beautiful checkerboard kind of pattern. So this is nothing but an interference pattern between three beams. So one pattern like this, other pattern like this. So what you see is the 200 by 200 nanometer by 500 nanometer is now divided into multiple spots of, let's say, 50 nanometer, 20 nanometer, something like that. So one thing you could see, there are bright spots and dark spots. So of course, first picture you take, so wherever there are bright spots, the fluorescence will be excited. Fluorescence molecules will absorb light and give you fluorescence. You will of course take the picture. And then there are dark spots, so you need to shift the bright spot into the dark spot. So that can be done with the help of a phase shifting. So they may be using the phase shifting technique here, or you can simply linear scan the grating. So then next picture you will take when the bright spot goes to dark spot. So then building the final image, and you will see this kind of structure. So in the white field, the same objective lens, if you have a single beam, so you will see the fluorescence microscope like this, hardly anything. But with the help of this technology, you could see fine details about the object. Background completely nearly finished, and fine structures of donut shape of all these typical kind of dead cells or something like that. You could see here. And you can also go to two beam version, and then they call it basically a kind of moire pattern. So in a state of calculating all the special frequency component, they rotate the pattern also. So for calculating 360 degree. So here is the comparison between the full width half maximum of this point spread function. So this yellow part is for wide field, and the red part, it becomes basically super resolution structural illumination microscopy. So you could improve almost 4 times resolution better this one. So this is the typical you could microscopic structure looks like that. Carl Zeiss. This is from Carl Zeiss microscope, but they are selling it very costly, something several crores of rupees, and all these things are there. So this is what is there. Structural illumination microscopy. So you can see the beautiful images comparison with the white field. This kind of structure is basically nothing is seen. This is myosin green fluorescence protein, actin myosin. Actin basically embedded with basically green fluorescence protein. With the bright field you could not see, but with the 3D SIM you could see all structure. That is the other one. So this is what is the great advantage of first technique. Means what has been done is basically the normal bright field microscope has been converted into a point spread engineering microscope, and that is via interference. And the interference pattern can be shifted. And the different pattern can be shifted. So first you excite the molecule, fluorescence molecule at the bright spot, and then the bright spot and take the picture, and then bright spot has to be shifted and take another picture, Normally four step phase shifting, and then they also rotate grating to structure 3D information. So they build very nice image. So this was the simplest technique to break that diffraction limit. And then next is coming very close to the quantum optics kind of phenomena by Stephen Hell. So you can see he made a very intelligent move. Look at here. So this is the first paper by Stephen Hell in 1994. The concept of stimulated emission depletion microscopy, STD microscopy, was first proposed and experimentally demonstrated in 1994 by these two scientists. So Stephen Hell got a Nobel Prize. So again, he uses everything same, but only very fundamental principle he applies here. Then what you see here is basically again same microscope, and of course sample on the fluorescence environment, fluorescence embedded sample. Then you have a excitation beam. Excitation beam shown here by this color, but the excitation beam normally in biology we use ultraviolet A. Mean anything below 400 nanometer we cannot use, because that ultraviolet light will damage again the cell. Our main purpose is basically non-contact, non-invasive, and to image delicate biological cell. So always the biologists use ultraviolet A or blue or green, 3 lasers for fluorescence. So this beam again same, and that perfectly collimated passes through these dichroic mirrors and focus through this again the powerful lens on the sample. And then of course they will be limited. So you can see the fluorescence emitted will be in this extreme right, you can see my cursor. So that the size will be again same, diffraction limited spot, this big, something like 200 by 500 nanometer. And all fluorescence molecule inside this will be giving you light. And the objective lens will collect all fluorescence from here. But what it did is basically injected another beam here. That beam happened to be, look at this. So this is the fluorescence concept. So if you have a blue photon exciting a green fluorescence light or molecule, so blue photon will be absorbed, the molecule will go to highest possible state, comes down, gives you green fluorescence. And this is what is the fluorescence, and without the second beam, STED, stimulated emission depletion beam, so that will be the fluorescence emitted. But with a clever synchronization, with a very, very clever synchronization of these pulse. So what is done is basically before all the molecules come down, after giving you fluorescence. So lifetime of this upper state is about nanosecond, 10 to the power minus 8 or minus 9 second. So if you inject before, so first you launch most of the molecule to the upper state, and immediately within femtosecond they will go here, and they take about picosecond time to arrive here, and that this lifetime of this level is about 9 nanosecond. So if you inject a picosecond or nanosecond beam here before they arrive here, so what this another beam will do is basically those molecules will be basically brought down by this beam, second STED beam, without emitting fluorescence. So, and then only few molecules will give you fluorescence. Rest they will be brought down by giving fluorescence on green color. So the concept is basically, they call it dark field, but a dark state. They call it dark state, but basically this beam is selected with, you can see here, the bandwidth, the energy gap between S0 and S1 is, let's say, delta E, and that beam has to be of this exactly same size. This depletion from here to here. So slightly smaller energy gap compared to the fluorescence gap here. So if you apply, so then those molecules will be brought down with the different fluorescence, different wavelength, and that can be filtered. And secondly, the beam, that depletion beam has to be made donut shape. This donut, central, nothing, but in the periphery, you have those photons of this beam that can be done with a simple phase modulation technique. And then the central part you can make as small as possible, very, very small, and put them together. So what will happen? All the periphery or major part of the green part of this will be basically molecules will be brought down by this deactivation via stimulated emission. And only the central few molecules will give you fluorescence at green color. This is what is the trick. So more clearly seen here. So you can see here again, you have the excitation beam. The green laser is used here, excitation beam, and which is above pulse width is 50 picosecond, and that focused on by this microscope objective on the sample. And the size again 200 nanometer or 500 nanometer. So all these will give you fluorescence by a the spontaneous emission, and that is basically diffraction limited. But if you launch this depletion laser, whose gap is just about this one. So from lowest to, so the gap should be smaller. Energy gap of this beam should be smaller than the fluorescence beam, slightly smaller than that. So it will give you different stimulated emission. So the pulse width, this is 50 picosecond, and that is also matching 50 to 200 picosecond. So both are launched like this synchronized fashion here. So what will happen? So and secondly, the depletion beams, the donut shape can be engineered, and you can leave this central part as small as possible. So only smallest part will be giving you fluorescence, green fluorescence, rest they will be giving you red fluorescence. And that red fluorescence can be easily filtered out in front of detector by applying another filter. So you just put a band pass green filter here. So you will see only the central green color, rest will be stopped. So suppose now from 200 nanometer, it has come down to 50 nanometer. So you could see, so now we need to shift this, the envelope across this everywhere. So you could build the image. This is what is done. So could you see the video down? Hello?
Yes, we can see.
Yeah. So what is done here is basically the combination of those two donut shape and that beam is basically scanned across the sample. So whenever, of course, there is some background also, but you see whenever there are fluorescence molecules, they will be picked up. So they built image with this one, and you finally arrive very nice super resolution image. And with this quantum, this basically you can say quantum optical technique, stimulated emission, depletion, dark state and bright state. So this is basically dark state. And then what they found is that the resolution formula of the lateral resolution is basically lambda by 2Na multiplied by under root 1 plus I upon I saturation. So it depends on how high powerful laser beam, that stimulated beam you apply. So this is the curve here, down see here, small of course, if you keep on increasing the intensity of depletion laser, then this ratio becomes bigger and bigger. So your resolution becomes much more better. So it is basically confocal is something like 250 micron here, and stimulated emission becomes just 48 nanometer. Sorry, 250 nanometer. Confocal microscope, same confocal concept. This is the diffraction limited spot, which is 250 nanometer, and you can see in this slide. And with the help of this STED and with this modified formula, you could reduce the spot size to 40 nanometer, an order of magnitude less size. So this is what is the new formula of microscope now. So modified Abbey formula, and which is given by this one. So depending on this ratio. So this is what is the STED microscope, very cleverly launching two beams, one beam just picking up for fluorescence from the smallest spot, and remaining periphery diffraction limited spot has to be the molecules have to be brought down by de-excitation via stimulated emission. So only central green part photon, only central green photon here will be emitted spontaneously. Remaining red photons will be brought down by stimulated emission depletion. This is what is the, so this is what you can see now. And with the help of this one, so this is what is the resolution structure. Confocal, this is a confocal for certain structure here, three colors of localized lamine, tubulin, and clathrin in fixed on those peak cells. And this is the confocal microscope. Same object, confocal means same setup, same set of components, everything same, but you cannot see anything. And despite the fact that most powerful lens, 100x magnification and 1.4 NA is used, but you cannot see. With the help of STD, you could see everything clear cut. So this is what is basically down to 20 nanometer. Resolution achieved in this STD microscope is 20 nanometers. So we could see single protein molecule or single molecule with the help of optics now, and broken the diffraction limit clearly. And now these are the more beautiful images of difference between confocal and all those things you can see very clearly. So basically from 200 nanometer to brought down to 20 nanometer resolution. This is the 10 times better resolution. Okay, so now this was the part of this one. Of course, some structural universal microscopy doing. What we are doing in this technique, we are doing in our green photonics lab in collaboration with the University of Tromsø, Norway. What we are doing is basically this kind of structures, biophotonics green photonics laboratory. So our nanoscope looks like this one. So you have again the laser beam. So because of course, the STD microscope is little more costly and little more difficult to handle because you have to synchronize two beams very cleverly. So we chose of first part, that structural illumination microscopy, and combining with the TIRF, total internal reflection fluorescence microscopy. The two combining, so you have the one laser beam divided into grating, so you can basically build an interference microscope like this one. This is basically Linux type microscope, closely resembling with the Michelson interferometer. So you can see 50% light goes to this mirror, 50% goes like to that sample, and both come back if the path L1 and L2 is equal or within the coherence length, they all will interfere. And in addition to that, we are basically exciting. So this part becomes holographic microscope or interference microscope. And the other laser we are launching here now, sample glass slide. On a glass slide, we build simply basically like PDMS or something like transparent material, few nanometer thick and 200 micron wide waveguide structure on a glass slide. Very simple technique. Then you can basically couple light from the side, and then you can basically excite the fluorescence. So you can see the fluorescence light, as well as with the help of this holographic microscope, you can basically compute the phase microscope. And then the total internal reflection phenomena well known here. You can see here if you have a light coming from the side, so with the angle is basically theta greater than theta c, so it will be total internally reflected. And but at the boundary of dielectric boundary, you will see the evanescent field. That evanescent field is nothing but decaying electric field, and we cannot see with the naked eye, but is basically fast decaying because light is an electromagnetic wave. So electric field of the light will be fast decaying, and the depth is about 200 nanometers here. So that kind of 200 nanometer height of the evanescent field is sufficient to excite the fluoropholes on the thin layer of fluoropholes on the sample stage here, and they will emit the fluorescence signal. And that formula is given by this one. So depth, that height of the evanescent field can be given by this one. So we chose, so there are other many techniques like simple single beam, like objective people use, and also you must have seen through prism, but we chose this one because prism, in the case of prism, you have only one point of interaction. Only one point. So if you want to see large area, so you have to scan the beam or scan the prism. But we chose waveguide structure on a glass slide on a silicon substrate. Then you can see there are huge area, a large wide field area of evanescent field. So you can basically image this one. Yeah. So this is what is the structure looks like. That is basically combining many this thing. That so you can see here the input light for holography is coming through this fiber bundle, and with the red, green, and blue, all three laser, helium neon laser and green laser and the ultraviolet or blue laser. Three lasers are there because you want to do multi-color super resolution microscopy. They basically pass through this fiber bundle with collimated light goes to this path. You can see the objective lens here, mirror here. So mirror is attached with the motorized stage. So 50% light goes to this path, that becomes reference path, and 50% light goes to this path, that becomes a sample stage. So from here, we are basically launching coupling the fluorescence light on this sample. So it is basically super resolution fluorescence plus holographic microscope. This is what is the structure. So you can see here, can show you what happens with this one. Just a moment. Oh. I think it is not visible. It should basically, it not running. So you could see basically how the beam, the excitation beam passes through the glass slide or waveguide structure here. So you will see multiple modes exciting. So those green photon will be exciting basically the blue basically blue light will be basically giving you green color. So this is the image of our paper on Optics Express. So this is how we do. So for computation, we use DStorm. this term direct stochastic optical reconstruction microscopy for this one. So our picture also looks like this one. So once you launch the beam from the side, so and scan the beam across the glass slide, so there will be fluorophore molecules, and fluorophore molecule, wherever there will be molecules, they will be basically giving you a very bright spot, and then we pick up several images, and we build image by this technique, and this is how it shows. So it is showing that this, suppose we have a nano structure of molecules like this one, and with a bright field looks like this one, with a stochastic direct stochastic reconstruction technique, you can build that all with nanoscope like this. So what is picked up is basically only the point spread function of each point here, bright spot. Rest of the spots, rest of the area is basically subtracted. With the help of this, you could see in this paper, you can see very soon in PNAS and multi-model technique for liver sinusoidal endothelial cells. And here you see those, the fenestration of these cells are very, very fine, about something less than 100 nanometer. So with the bright field microscope, you cannot see. Here is a bright field microscope but in this our super resolution microscopy, you could see all fine fenestration of liver sinusoidal cells, and this is more clear. So it is by size of fenestration present in this is basically 100 to 150 nanometers. So all details are seen. So with the bright field, you cannot see anything here. This is how we build the image, and then we can, of course, our technique can also see the nanostructures on a glass slide as silicon. So this is what is the nanoscopy about. So okay, what is the time now? Hello.
Yes, Professor Mehta.
Yeah. So what is the time?
6:05.
So how much time I have now?
You can take around 5 to 10 minutes.
Okay. Okay, I'll try to finish the other part. Till now, I have been speaking about only nanoscopy. So this is also we are very much working in this phase microscopy. So you know, now in the beginning I showed you two techniques also awarded Nobel Prize in Physics, Jernak's phase contrast microscope, and this what is called Gabor's holographic microscope. So look at this one. You could see here, long back in 1936, around 1934, yes, 1934, he invented this microscope. So again, same microscope, everything same. But you see, this light beam is basically passing through this annular aperture. Annular aperture, which is basically light will be now, uniform light will become a ring pattern. A ring pattern passing through this condenser, and this focused on the specimen. So what will happen? The specimen will basically scatter light. Specimens on a glass slide, most of the biological samples, in the thin layer of biological sample, they are transparent in nature, nearly transparent. They don't absorb light significantly. So for any imaging or microscopy, the contrast has to be very high. Means the intensity at 0.1 should be, let's say, some value, and next point it should be minimum. Then the contrast becomes very high. So he did kind of interference light of light. So what will happen? That ring pattern, of course, after shining light on the sample will scatter or diffract light. So this pink color light is diffracted, and then yellow color light is basically direct light. So yellow color light becomes a reference light, and that pink color light becomes a object light. So with the help of all this, they are made incident on the image plane, and they will interfere. And due to this interference, so this is basically interference contrast microscope without fluorescence. So all I have spoken up to now is all fluorescence microscopy, but now we are going to the different domain without fluorescence. So another requirement in biology is that, if possible, without labeling any biological specimen, if we can image and if we can compute various parameters, then that would be the finest one. This is what is the next stage. So without fluorescence, can we see the fine structures of the object? Answer is yes. So look at this is a bright field image of some biological specimen on a glass slide, thin structure. And if this, if it is seen through the same microscope, it looks like that. This is a much more details about all cell boundaries and cell nucleus, everything is visible, and which was not visible with the help of bright field microscope. Of course, you could see with the fluorescence microscope, but fluorescence we'd want to avoid, because fluorescence again adding some external contrast agent, sometimes not very good. So if possible, we can do that without fluorescence. So this is what is the Jernak's phase contrast microscope, and this is simple interference pattern, and that is also common path interference. So this is what is the beginning, and more details can be found here. And almost similar thing was done by Gabor in 1948. So you can see here he published a paper. So without, what is the difference between these two? Here a series of lenses are there, combination of 1 lens, 2 lens, 3 lens, 4 lens, so many lenses are there. Gabor did this almost without, hardly with a single maybe lens. 1 lens he might have used for focusing light on the small spot. After focusing here, so beam will be dispersed, and sample you can place here. So surrounded beam will become a reference beam, and the scattered light from the star object will become scattered light, and they propagate the same path, and they produce the interference pattern. So that interference pattern is recorded. So both the configurations are common path and use low coherence light source, hence highly stable and speckle free. Both the techniques are label free, no need of exogenous phase contrast. So it means fluorescence microscope, of course, fluorescence molecules are added to increase the contrast actually. And sometimes, of course, they give you molecular specification because binding. But if you just want to use fluorescence, so fluorescence is used for contrast improvement. But what we are seeing is that contrast improvement in the samples can be also done simple interferometric technique, that to common path interferometric technique. So this is the beginning of quantitative phase microscopy. So this, but now modern, so this has been not very popular after. In between, of course, DIC is well known, all those things. But after 1990, this became very popular. You can see here, this with the help of computers, CCD camera. Now the same techniques or started by Gabor and Jernak. They call it quantitative phase microscope. So what is shown here is basically with the help of the computers and CCD camera programs, we can do a lot of calculation about the sample. So what calculation? Cell morphology you can do, hemoglobin concentration you can compute, cell dry mass you can do, refractive index distribution. These are the static parameters, that too without disturbing the sample. You just prepare sample on the glass slide or in the media, and you can also monitor this cell growth, dynamic properties of the particle, like cell growth, cell motility, cell membrane fluctuation, deformability study. Bioelasticity is very popular. Cell dynamics, like say, what is the bioelasticity? Like in our body, there are so many microstructures, microtubules, very small size, and the size of the RBC is about 7 micron diameter, 3 micron thickness, but the blood cells have to deliver oxygen to every part of the body. So what they see, whenever they find very narrow passes, the cell basically folds and still delivers this one. So this is what is so if the cells are healthy, their bioelasticity is very good. So they are very much elastic. They can basically propagate and do the job. So how to monitor this? So all these parameters are calculated with the help of quantitative phase microscope now. And what it is basically, you can see here, if light passes. So sample is prepared only the glass slide, but suppose you have a glass slide here, and then let's say one cell, let's say RBC, then and in the surrounding medium, let's say water or something like that, or may not be water. So if you have a plane wavefront passing through this cell, and this cell plane coming from the top, and then the wavefront will be delayed. So this delay in wavefront can be easily measured with the help of the quantitative phase microscope, like this one. So variety of cell, normal erythrocytes look like this one. So their phase delay, when light passes through entire cell, the phase value of these cells will be different. When you have some kind of erythrocyte containing less hemoglobin, their phase value will be less, refractive index will be less. And many times this sickle cell and morphology is basically changing. Normal cells look like this one, spherical becomes like this, and oval shape, sickle cell becomes like this. So how to quantify, let's say, hemoglobin, dry mass, all these features with the help of this quantitative phase microscopy. And plus there are other features like malaria, cancer cells. So like macrophages, sperm cells, human embryo, all these techniques need to quantify without adding any fluorescence. You cannot add fluorescence here, macrophages. You cannot add fluorescence molecule here. You cannot add fluorescence molecule here because this is important for IVF technology. And this is important for IVF technology. So no fluorescence microscope will work. And phase contrast microscope also do not give you good picture. So what is the solution? Solution is only quantitative phase microscope to quantify them. Quantify the biophysical parameter, the refractive index, hemoglobin concentration, phase value, height, morphology, all these parameters need to be done. So there are a variety of cells where your fluorescence microscopy is not allowed, and forget about AFM, SEM, TM. So the quantitative phase microscopy is the only technique for this kind of cells. So we have done a lot of work in this, our macrophages, cancer cells and sperm cells, and now we are doing a human embryo. And what is the quantitative phase microscope? Our looks like this. So quantitative phase microscope is basically a magenta type of structure, interferometric microscope here. So you have a helium neon laser beam coming from here and sample here. So this becomes a sample beam, this becomes a reference beam, and then you pick up the interference pattern and you basically compute the phase map. And this is a white light microscope here that I will show you later on. So, and this is another kind of phase tomographic system. So they are all level-free microscope. Some people build like this one, diffraction phase microscopy. Our microscope looks like this one. So you can see here, we don't use laser. Again, laser sometime, if you have a high power, tightly focusing on the sample, sometime it may also damage. So what we are using is a white light interference microscope. In this white light interference microscope, there is a very compact interferometric device here. This compact interferometric device is basically, you can see light coming from here, 50% goes like this one, 50% light goes down and comes back. They both interfere and you record the interference pattern. And interference pattern looks like this one. So I can show you more. Okay, just a moment. Yeah, see, you can see, could you see the picture here? Extreme right? Hello?
Yes, we can see.
Yeah, so you see that this is the interference pattern of red blood cell on a glass slide. So you could see the, I'll change the phase of this interference pattern. So you can see, yeah, so the interference pattern is shifting. This is how it is happening. So we record like this. So there is nothing required, no addition, nothing, no fluorescence, nothing is required. So you could basically see the interference pattern of the cells, and these are all RBC, and without doing anything, and you apply the phase shifting technique. With the help of phase shifting technique, we can basically improve the resolution as well as compute various parameters like this. So we also do further analysis because these pictures are captured with a color CCD camera. Your white light interference pattern is a combination of 3 colors, basically red, green, and blue, and you can basically digitally separate them. You can compute the phase map, and phase map, after the phase map, you apply these formulas and you can basically compute this height variation. You can see here for red color, we could compute refractive index 1.386, for green color 1.395, for blue color 1.4. It is basically giving you higher for shorter wavelength. So this is what is our phase microscope. Quantitative phase microscope, which has better resolution as well as quantitative quantifying. And we also use for this cancer cells. You can see cancer cells from the hospital, Ames Hospital, done so many samples. So you can see normal cell look like this one. This is again white light. So you can see beautiful white light color. So you can basically divide into RGB and you can compute refractive index. And then you can basically do this kind of, so this is cancerous, this is basically normal. So we are basically classifying with the help of our quantitative phase microscope. Otherwise, other people also use this Mach-Zehnder or Linick type of interferometer. And actually, what just another 5 minutes I would conclude. So first part, our microscopy is basically, of course, we are doing nanoscopy. Apart from that, we are also doing level-free white light interference microscopy. But we also are working on phase microscopy using lasers. So all the phase microscope, quantitative phase microscope all over the world, they often use only helium neon laser or a green laser, large coherence length laser. They always use, and the interferometric microscopes look like this one. So what is the problem with this laser? Problem with this laser is basically because of the long coherence length and high spatial coherence, you will always see this kind of speckle patterns, spurious fringes, even though the quality of all the optical components is very high, but you will always encounter with this kind of phenomena. Can we eradicate this in a laser-based system? Answer is yes. So this is our microscope. Our microscope, we wanted to compare. So our microscope, holographic microscope, looks like this one. So you have all green laser, helium neon laser, high coherence length laser. We have a LED light source, and then you can see this laser beam passing through rotating ground glass. So we use partially spatially coherent light, and that goes to this microscope of the fiber bundle. And one beam is direct coherence, high coherent light with a single mode fiber, because if you couple a laser beam through the single mode fiber, its the coherence property remain intact. And then we are using here both partially coherent light from this path and highly coherent light from this single mode fiber. Both are launched to this holographic microscope simultaneously, and we wanted to get rid of this phase problem, that the speckle problem, spurious problem, and we succeeded. And this is what is the result. Look, all over the world, people use helium neon laser or a green laser for imaging, for quantitative phase imaging. So here is a waveguide structure. Same microscope, everything same, only light from single mode fiber is switched on, and partially coherent light is blocked. So we cannot see anything. So if you zoom it, so you will see a lot of spurious fringes and non-uniformity of the fringe pattern. But at the same time, we rotate the ground glass, you could see fine details of the waveguide structure with nanostructures. So see, looks like a magic structure here. Of course, this is with the bright field or LED. But if you compare highly coherent light and partially coherent light, same laser, same setup, everything same. So highly coherent light cannot see some fine features on the object because of the speckle pattern and because of the spurious fringes. And at the same time, if you make it partially spatially coherent, you could all visualize all fine details of this one. So now let us compute the phase map of this one. Of course, this is not. So let us compute the phase map. So phase map across the mirror. So just using no object, only mirror, fine polished mirror. In the mirror also, because of various components in the system, you will always see the pattern like this one with the coherent, highly coherent light. So people will always prefer high coherent length should be there, high spatial coherence should be there. But in the realistic application, this high coherence is always a problem. So see the spatial phase distribution here is maximum 0.2 or 0.3. At the same time, across the space, how much phase is varying across this space along x and y axis. And in the case of coherent light, it is 0.3. In the case of partially coherent light, it is 0.02. An order of magnitude better result with partially spatially coherent light. This is, and if you want to measure the height, basically suppose I have a nanostructure, then I'm using, I want to measure the nanostructures, few tens of 20 nanometer height of the waveguide structure using coherent light. I will not be able to measure it. But with our light, you can see up to 1 nanometer, sub-nanometer. This is what is the big achievement we have done over the quantitative phase microscopy. So this looks like the red blood cells with the coherent light microscope. You could see red blood cell, of course. You could also see the very good fringe pattern, but the fringe pattern is cluttered with the non-uniformity. Bright, dark. But but at the same time, partially coherent light looks like this one. So phase map of this will be at least an order of magnitude better than this. This is what is the achievement from our lab. This is of course showing to show the speckle effect. So if speckles are there, very heavy speckles are there, like RBCs will be totally blocked. And at the same time, if you just rotate this, everything same. You record with heavy speckle, you would see nothing because of the high coherence. But now you reduce the coherence, and you could see the same setup here. 1, 2, 3 fringes, 1, 2, 3 fringes, but you could see RBC here. So this is the difference between our technique. So we are all using partially spatially coherent light in our quantitative phase microscopy, in which we observe an order of magnitude better resolution and better spatial phase sensitivity. Look at this one. Like I said in the beginning, sperm cell is basically quantification of sperm cell is very important. And for IBF technology, with our coherent light holographic microscope, we could not see the tail of the sperm cell. Only the head could see visible here. But at the same time, if you switch to the partially coherent light, you could all the way see up to the tail. And you could reconstruct the phase map and can quantify. So this is the difference. So you can see the phase value also 0.3 here, maximum 0.02. Order of magnitude phase improvement. And then we can, of course, do a lot of computation about this state. This is the same sample, everything same, but you cannot see hardly, you make, okay, there are two heads looking like this, but you can see here, clear cut, all the tail. So this is the power of partial spatial coherence digital holographic microscope. Then we did a lot of computation for this and gave the lot of parameters to the IBF technology that in Tromsø hospital. And then of course we are doing microphases also, phase microscope. I would like to stop here. So all these results are basically published in these journals. Most recent one, 2020 only, you can see. And then little earlier versions are these one. All these basically speckle-free digital holographic microscopy and chip-based nanoscopy. So you can see all these. So what we have played here at this end, I can say is that two things we have done. One is in nanoscopy, simplest waveguide structure-based nanoscopy. Second, in the holographic microscopy, rather than using pure highly coherent light, we can use partially spatially coherent light and achieve an order of magnitude better phase sensitivity and better height measurement and compared to coherent light. So all over the world, they all often use only highly coherent light. So our results are very, very important. Thank you very much.
Thank you, Professor D.S. Mehta, for the wonderful talk.
Sorry for too much delay.
No. It was very nice. Yeah, you covered the basic. You started from the basic. You took us to the history, like how it started for both the fields. So I have many questions, but before I look at the Q&A box, so there are participants who have posted their question. So they're complimenting, saying that thank you for the very nice presentation. What is the resolution limit of AFM and SIM? That's first question.
AFM and
SIM.
SIM. Okay. SIM is structural illumination microscope. AFM is basically atomic structure, angstrom level. AFM is atomic structure. Depending on the tip, how sharp tip you can make is basically can go to atomic level, mainly angstrom level. And you can simply see the single atomic defects. And I showed you in the previous slide that the very first slide, the defects in the graphene, 2D graphene, you could see atomic structures you can see with the AFM. And SIM, structural illumination microscopy, is bright field microscope gives lateral resolution 200 nanometer divided by 4 times you can achieve. Means 50 nanometers or 100 nanometers you can achieve. 2 to 4 times, depending on how, between 2 to 4 times better resolution of using SIM compared to bright field microscopy. So you can see basically 100 nanometer very easily. If you have a wavelength of light of 500 nanometer, this is what is there. Yeah.
Second question is, what kind of wave is used as the outer beam, hollow shaped beam in STED? Set.
What kind of?
Wave is used as the outer beam or hollow shaped beam in STED.
Yeah, this is basically hollow beam is another de-excitation wave. Basically, if you have a, he is talking about wave is basically collimated beam. It is collimated beam. You should say always collimated beam. It is all the way light wave basically, and collimated beam, but central hollow surrounding basically that depletion laser. Depletion laser means if you have a blue light exciting fluorescence peak excitation is 532 nanometer. So you could use next wavelength slightly longer wavelength than 532 nanometer, something like, let's say 580 or 590 nanometer. Then you can bring down all the molecules from the upper level to down lower level with depletion stimulated emission. This is what is the feature of the STED beam.
So
wavelength has to be slightly longer than 532 nanometer, means fluorescence light. The shape of the beam should be donut, and the central hole can be as small as possible depending on your capability. And the beam laser should be pulse laser. Both excitation and depletion laser should be pulse laser. These are all features of that beam.
thank you for that. Next question is, hello, thanks for the excellent talk. Can you give some information on the typical temporal resolution of the super resolution microscopy?
Oh, okay, good question. Temporal resolution depends on the detector. It is a very good question. Next thing people should do in this nanoscopy is the high speed nanoscopy, ultra high speed nanoscopy. Right now, temporal resolution is maybe they may be using just a normal EMCCD camera, something like that, which is about millisecond time frame or frame record. So this is important. I think I also never thought of this. Just now I coming to my mind. So can we make really this nanoscope, let's say STD nanoscope, super ultra high speed nanoscope? Answer is yes. If you use streak camera or ultra high speed framing camera, how much high speed? Something like million frame or billion frame per second. So you could virtually see the atoms, the molecule absorbing light, of course, will go to high this state, but fluorescence decay. Fluorescence nanosecond event you can see. The fastest event you can see with the existing ultra high speed camera or streak camera is basically nanosecond event. Then you can really see the God in the particles. It's too much. Right. Super resolution as well as super temporal resolution. What is the name of person who is asking this question?
He's Murli. He is a PhD student at IIT Bombay.
Yeah, Murli, you should equip your super resolution microscope STED for. Basically, you should go for this STED, and then you would be able to record the fluorescence decay and depletion laser decay with the high speed camera. But that high speed camera comes, let's say, 2 crore rupees, not less than that. Okay, so this is a very important question. So means super resolution can be super temporal resolution as well. And what is the highest temporal resolution? Shortest event you can notice is basically transition from upper level to down level of that nanosecond. If you have ultra fast, then you can of course go to picosecond level, but you could virtually see the fluorescence decay. Yes.
Yeah. So I think those are the questions in the Q&A box. We had circulated the registration form, so there were some couple of questions there. So they are generic questions because that's on the topic and that. So one of the questions was why all the cost of all these microscopes, the special microscope, are very high.
Yeah.
And is it possible to bring down the cost?
Right. So all these microscopes are built by American, German, and Japanese. Understand? That is another important question. They are made by these people. Their labor cost is very high. But if we think of, if you want, suppose I'm thinking of making one, so I would make a nanoscope one within 1/10 of the cost what they sell. What is done is basically we should have a perfect engineering skill, and the components, the highest quality components, they are available off the shelf. That's it. And they are very, very low cost. So what is adding cost is total, labor cost kind of thing. Otherwise, the component do not cost too much. This is
So
what
can we say that is more like a IP cost? That is the cost of the IP that they are charging.
Yeah, that is also true. That is also true. But once Nobel Prize is given, that the IP does not remain valid, so you are free. So
Okay.
both the things cannot go together. Either you talk about IP, the people should go for IP or go for Nobel Prize. So if Nobel Prize is given, then you are free to build anything. It's open. It's open science, no? Now.
So like I have one question regarding your last part where you spoke about this partially coherent.
Yes.
So just trying to understand, like, how did you reach, like, how do you came to that? Okay, you should use, instead of the highly coherent light, what everybody in the world is using, you should go for partially coherent. So can you give some background? Like, how?
Yes, it's very good question. Very important question. Those I would basically advise to all the audience, whoever is going to build a holographic microscope. So please read our papers. Our papers clearly show an order of magnitude better measurement capability than highly coherent laser sources. So when question came, how we came, because I have been in this field, means partial special coherence field, since my PhD. So my PhD is basically wolf shift. Wolf shift means special coherence effect on light source. Effect of special coherence of light source on the propagation field. This is the PhD title of my title of my PhD work. So from that, I am in this partial special coherence. So once I was making this white light interference microscope, because I knew that the coherence will be always a problem. Then I thought, because of course white light interference is also popular, quite appreciated. But since most of the phase microscopy people, they prefer laser, so I thought of implementing my early version of my knowledge in partial special coherence in this phase microscopy, and it turned out to be magic. So I am writing you can see my Google Scholar, and the latest 2021 one review article I have written, my student, on this partial spatial coherence is not only this microscopy, it is also for fluorescence microscopy, for projection imaging. In future, people will see laser based projection television, projection cinema, projection laser show, all these things. Wherever you are going to use laser, there is a problem of speckle. So all of you can read that speckle-free projection imaging, fluorescence microscopy, holographic microscopy. I am also writing another grand review and covering all the holographic phase microscopy with partially specially coherent light. So adding to your question, because you raised a very important point. So now you may think, why, if I am using white light, then why should I go to laser? So using white light to realize a Mach Zehnder or a Michelson interferometer is pretty difficult, much difficult. So laser, being a long temporal coherence length, something centimeters or several hundred micrometer to centimeters. So temporal coherence is not affected much by our technique. It is only the spatial coherence affected. So you can build very easily the Michelson interferometer based holographic microscope, or a Mach Zehnder interferometer based holographic microscope, even though you have basically reduced the spatial coherence. That is what is the important part.
Okay.
Yeah.
I think those are the questions that we had.
Yeah, thank you very much.
In case if any panelists